so we had advising starts today. Yeah, it does. Right? Registration's not until end of the month. But the website, the biology website's not correct. So this was one out. There should be posters or sheets set up, so could have changed. Here, honor students, yes, not pre-Hill, it's still Dr. Grugo.
Oh, really?
Dr. Ammerman's the grad student advisor. You should probably talk to your PI though, whoever you're working with. I think that's Dr. Ammerman might ask. Did you talk to your advisor? And any degree planner problem goes to Dr. Dixon. I hate to say it, if you don't know who your advisor is, go talk to Dr. Dixon. That's mean. He's going to be swamped no matter what. Do you have a question?
Yeah.
Yeah. I think I did M through something. Maybe R, Q and R too. I don't know, but I got so we were told. So that I think this is who had some changes, but we were told if you had been advised. So I'll use Cody. Okay, yeah, Cody was my advisee. If he was an undergraduate again, I no longer had the P's, but they said that if you've been advising someone and they still want to get advised by you, that's fine, you can do it. So we're just spreading the work around a little bit, I guess. So check the sheets that are posted. Who knows when the website will get updated. That's that. I'll close that out. And next up, homework. There it is. Homework probability. So a couple of you had emailed me, and that's fine. But I went ahead and made a submission. So when you do the probabilities by hand, or if you do it in R to calculate it, you can upload it right here, so that way you don't have to email it to me. I will say that Blackboard was incredibly slow today. So by the time I hit submit on the grade to go open up the next one, the web page opens up, let's say in 3 seconds, 5 seconds, but then it took like another almost 10 seconds, easily 10 seconds, maybe 15 seconds to actually open up the PDF. I mean, just it's a killer. Something that I could easily flip and be done. Just killer. Anyways, that probability's up. I also have discrete and the discrete distributions, so binomial Poisson distributions. This is set up as an RMD file. And I do have one more that's like meant to be done by hand, but you can use R or do it by hand. How we're going to do it with quizzes and exams will be, I'll ask the question and then fill in the blank to write the probability. All right. Or I'll give you options and select the answer. And that'll be tricky because if you make the common mistakes, then that answer will be on there. You'll make a common mistake and say, "Oh, there's the answer." So you're wrong. That's how you can be tricky. So I do think we get through this hypothesis testing and confidence intervals by our next exam. So our exam will include this. So you're going to see us kind of move a little bit quickly through the discrete distributions and also through the normal distributions. Learning how to do these probabilities really isn't difficult, especially if we're using R. So let's talk about things. So I said the homework, that homework number 4, if you haven't submitted it, have it done and submit it on Wednesday. I've set the time for like 4 o'clock, so if you have questions, if you were unsure how to answer one of the questions, you can bring that question to class. If you're going to be doing this virtually and a question comes up, what you can always do is email me before class, and then what I'll do is I can address it in class in case other people had the same types of questions. So, go over discrete random variables. So we started to introduce binomial distribution. And what we've done so far is we've used some of this binomial distribution as our introduction to just probabilities, using our multiplication rules, using our addition rules, and so forth. So one thing you can remember with this is that the same rules apply. When we have to have so many things that happen, so many successes, and so many failures that have to occur together, we have to multiply. But the difficulty comes in accounting for all the different ways in which it can happen. All right. So if we think about, the daily lottery, the daily pick 3. All right. It's drawing 3 numbers between 0 and 10. If you ask, what's the probability that we could get 1, 2, 3 as the daily pick 3? Well, if it's in that order, it's just straight multiplication. But what if we just said, what's the probability that the daily pick 3 includes the numbers 1, 2, and 3? Then it could occur in any order. And the question is, how do we figure out that combination, those number of combinations? So for that, this is where we have our equation. All right. So the probability of getting k successes in n trials, or what I'll do is k of n. All right. We use this equation where we multiply the probability of success by itself any number of times, however many successes. So probability of success raised to the number of successes. This tells us how many events must happen. And then we multiply 1 minus p raised to the not event, so the number of events that can't have successes. All right? And the n minus k gives us that number, because the out of number is that n trial. So out of how many trials, we subtract the number of successes to figure out the number of failures. And then this thing, this n choose k, that's our choose notation. This notation tells us how many combinations we have of k and n events. Okay? This is the easy way to calculate something like this. Make sure it's not there. And you've seen this before. You guys recognize this? What is it? So what? Pascal's triangle. This is our number of combinations. So it just keeps going up. So if we made this big triangle, all right, where one's on, this number is the sum of the 2 above it, this number is the sum of the 2 above it, this number is the sum of the 2 above it, and so forth. All right. This gives us our expansion. So the one that you've probably seen is, the quadratic formula, right? P squared plus 2pq plus q squared. That's a binomial trial. That's a Bernoulli trial. It's 2 outcomes, dominant or recessive allele. Where do we get our combinations? P squared, 2pq, q squared. All right. If we add a third allele, all right, we can expand it into, a cubic. All right. Now, what we're going to be working with is, when we do the out of notation, there's a possibility that we're going to be all the way down near at the floor. And trying to draw out this triangle just isn't realistic. That's why we use this choose notation. This choose notation is going to calculate how many different ways we can have k and n outcomes, or k of n outcomes. All right? So the way we use it, is use the NCR button. NCR. So N choose R. Now, we could do it by hand using factorials. Or we can use the calculator. All right? So let's check that out. All right? So we can do this. We use 1, 3, 3, 1. That's what we had. We had 3 fish. You can have 0 successes, 1 success, 2 success, or 3, all 3 fish being infected. That was our outcome, right? And we showed by brute force how we got that 3 and that 3. We can do the same thing using our calculator. So the way it works is to take out the total number of trials, so the of trials. You hit your NCR button, and then you do how many successes you want, all right? So on your calculator, you should be able to find an NCR button. Mine is above one of my buttons, so I access it using the Shift key. I have to use Shift and then the division key to get to NCR. So on mine, what I would do is 3, Shift, NCR, and 1, and hit equals, and that gives me 3. All right? Yours may be a little bit different. All right? You may need to access the stats or the probability menu. So if you have like a like a TI-84 graphing calculator, you're going to have to go to the math and then the PROV button to find the NCR. The probability keys to get that NCR. It's not NPR, it's NCR. N choose R. Total number of trials, we're going to choose our number of successes. All right, so if you did 3 NCR 1, you should get 3. If you did 3 NCR 2, you should get 3. If you do 3 NCR 0 or 3 NCR 3, you're going to get 1. You can do this one, 4 choose 2, and see what you get. So I can do 4 NCR 2, and I get 6, which is what we came up with here. Right? In R, if we wanted to do it manually, there's a couple different ways to do it. All right? One is to actually use our equation, and that is this equation with all of the factorials. So you'd use your factorial n divided by factorial k in parentheses. So divided by, in parentheses, factorial k times factorial n minus k. But that's long because R has a built-in choose notation, which is choose, parentheses, n comma k. So go ahead and open up RStudio. And we are going to be needing it. For probability, I am going to make a new markdown document. Over. All right, so there's 2 distributions that we're going to work with. We're going to do the binomial distribution and the Poisson distribution. Those are the 2 that we're going to work with. We're going to start with the binomial distribution. All right, so binomial distributions, you're asking probability of k successes in n trials, so k of n trials, where p is going to be our probability of success, k is the number of successes that we're trying to model, and n is the number of trials, all right? So choose notation here tells us the number of combinations of k successes in n trials. All right, so we flip a coin 10 times and we ask, what's the probability of getting 4 heads? All right, that's 4 successes, 6 failures. But those 4 successes could come in any order. We could have 4 heads right off the bat and then 6 tails. We could have 6 tails and then 4 heads to end it. Or we could have any possible combination of that. All right. So what we have to do is figure out those combinations, and this is where that choose notation comes from. So choose is going to be in the format n comma k, where let's fix this up. So the function is choose. Example. How many ways how many ways can we get 4 heads out of 10 flips of a coin? That's going to be pretty easy, all right? It's going to be pretty easy because our function's easy. So we've got 10 flips. We want 4 successes. I hit play and I get 210. There's 210 got different combinations to get 4 heads out of 10 flips. All right, 4 heads out of 10 flips. It's crazy. That's crazy. Can we confirm it with our calculator? Oh yeah. Try it. I got 10, choose 4. I get my same answer. All right. This beats using products and the division and factorials and so forth. All right. We have it. We have the choose notation in R. Let's just use that. Now, about the only time we would use that in R is if we ask the specific question, how many different ways can this happen? Right? And the reason I say that is because R has a built-in probability calculator to do the binomial distribution. We've already introduced you to some of those distributions, some of those probability distributions. Now we're learning about the binomial. So on those distributions, remember, we had that very first letter started with an R. It could be an R value. That did our random number generator. Right? The P gives us a percentile. D gives us a probability. Right? It's a density. Right? So for us, we want to go back and revisit this fish example. All right? So we sampled 10 fish, and what's the probability of getting P, or what's the probability of getting 3 infected fish out of 10 total fish? So we've changed it. Instead of 3 out of 3, now we've increased it to 10. So mathematically, we've asked 3 successes out of 10 total trials. All right, that's what we asked. So now, using our recognizing that this is a binomial distribution because we only have 2 outcomes, success or failure, infected, uninfected. All right, we're going to do 10 choose 3. That's going to give us how many different combinations we have of getting 3 infected fish out of 10 total. All right, and then our probability of being infected is 10%. We're going to raise that to the 3rd power because we have to have 3 of those that are being infected. And then we've got 90 raised to the 7th power, because that gives us lost the train. I'm sorry. All right, so 10% because that's what had to be infected. We needed 3 of those, and then 7 of them had to be uninfected. All right. So on the calculator, I can do this all in one line, and I kind of wrote out how to do it. So this is on my calculator. Your calculator can vary, can differ. So I'm going to use 10 NCR 3, use a multiplication. So right now, I know that I have 120 different combinations. Then I'm going to do 0.1, so 0.1, and then x raised to the y to get to the third power, times 0.9 x to the y, 7. So I know I have a number. Got a number on my calculator. Now we can check it in R. And R is also pretty easy. So R, we're going to use the d binomial function. This gives us the probability of getting 3 successes out of 10 total trials. In this case, we're asking 3 infected fish out of a total of 10. All right? And we're going to use the d binomial function. So I'm going to go back. Get that? Did you finish with the calculator? So that 0.1 x to the y and 3 gives me this. Calculator is going to do order of operations for us. Raise the power before exponent before it multiplies. All right, so in R, so probability of k of n trials can be calculated using the d binomial, the density of binomial. Now we're going to do k successes, n trials, and prob. I think say prob or probs. Prob. Tricky. All right. So kind of define our variables where k is number of successes, n is total number of trials, and prob is the probability of success. All right, so example, what's the probability of getting 3 infected fish out of 10 if the probability of infected is 0.1? So that's our question. I have d binomial, 3 infected, we're out of 10, prob 0.1. All right, just kind of lay it out right in order. And it gives us our help, so I'll open those up and kind of look at it too. But I'm going to run it, and I get 0.0573953, which is the same value that I calculated on my calculator. So for those of you at home, there it is. Yep, I can see it. All right. So take a quick peek at our help file. So if you weren't sure in which order you needed to place things, you can always take a look at the help file. So, right, I opened up, I went to the help tab, started to type in the function d binomial, and it opens up my binomial distribution. So it tells us we can calculate the density, the distribution function, quantile function, and random generation for the binomial distribution with parameters size and probability. So this distribution is defined by the size, so the out of number, and the probability of success. Yep. And it says even here in the help file, this is conventionally interpreted as a number of successes in size trials. It's probably the easiest way to describe it. So we have 4 different ones: d binomial, p binomial, q binomial, and r binomial. all right? And these are all a little bit different. So our binomial, that's our random number generator. So we can randomly draw a certain number of samples n from the binomial distribution defined by the size, so the out of number, and the probability of success. P, we're going to encounter P. That's a area under the curve. So basically a less than or equal to number. All right. So if we ask what's the probability of getting 3 or less infected, well, we can use P binomial to do that. And then Q binomial kind of gives us our cutoff. So if we wanted to know what's our 95% cutoff for this distribution, that's what our Q binomial would give us. Are we ever going to use that Q binomial? I don't think we do. I don't remember using Q binomial at all. But we will use D binomial, and then just briefly, we'll see P binomial. There's another test that uses it, and we'll just demonstrate that the test gives us the exact same answers if we did it by hand. All right, so D binomial needs x, comma, size, comma, prob. And then there's this log equals false. We ignore log equals false. That's asking if the probabilities are reported as a log. They're not. We're just going to be working with raw probabilities. But x gives us the vector of quantiles. That's our success. How many successes do we have? And so I've kind of changed it to say k of n to match the equations that I have on the board, match what you would probably find if you look this distribution up online. All right, size, that's our out of number, and then prob is the vector of probabilities, number of observations, the total number of trials. So if you are unsure how to use this, go ahead and you can look at that help file. All right, so we do have one practice problem. So on this problem, we have a clutch, we have 8 offspring. All right, we want to know what's the probability of getting 5 females out of those 8. All right, so we can do it by hand, or we can do it in R. Now, this is where this year is different, because you can't really say that you have to use your calculator, but do what you want. All right, so I gave you the code in R. You can type it out, you can kind of clarify it, but check to see what the answer is. Let's do this too. All right, you get it? Basically just copy and paste just to make sure that we have it. All right. So what did you get? .21875? That's what I got. That's what I got. All right. 2 more, just to check. I guess I did my practice 1 and 2, so I guess this will be practice number 3. All right, so first question. All right, so we have a bag of marbles. We'll just arbitrarily say we have 25 marbles in that bag. All right. And the chance that we're going to draw out a red marble is 0.2. We can actually change that. Let's just change that up. Let's make it easy. Let's do 100. We have 100 marbles in a bag. Probability of drawing a red one is 0.2. All right. From that bag, we're going to draw marbles. We're going to draw one out and record it and put it back. All right. So we're going to sample with replacement. What's our probability of drawing 8 red marbles if we're going to have a total of 12 draws? So 8 out of 12. Question mark. All right, that's practice number 3. Work on that. And you can do it by hand or you can use R. R off to the side. Did you get it? So instead of writing everything out, we put it into mathematical equations. So what's the probability of 8 successes out of 12 total trials if we have a probability of success equal to 0.2? All right, we're going to use the binomial distribution. That out of is a clue that we'll use the binomial distribution, along with the fact that it's either success or failures. All right, so d binom 8, 12, prob is 0.2, and I get a pretty small number, 0.0005. All right, did you get that? All right, do we need another one, or does this seem pretty easy? We've got some homework problems that will give us a little bit more practice. So let's move on. All right, so this probability, binomial probability, is defined by the total size, the n, and the probability of success, p. All right, from these numbers, we can get a measure of the location and the scale of our distribution. So our location, our central tendency of this distribution, is going to be defined by the product of our total sample, or total number of trials, times the number of successes. Okay? So we can look at this example, this 8 red out of 12 marbles. All right? We had 12 total marbles. All right, that's our n. Our number of successes is 0.2. All right? What is that product? What is 12 times 0.2? I think it's 2.4. 2.4? All right. All right, that's our average. So if we have 12 total trials, if we draw out 12 marbles with replacement out of that bag, and the probability of success is 0.2, we expect on average to draw 2.4 red marbles. All right, and that's kind of important, all right, because it tells us the average, our average expected value, depends on that probability of success. It's going to be centered around whatever that probability is times total number of trials. Our variance is defined by n times p times q. So now we take into account the probability of failure too. Now what does this have to do with our distribution? Well, this figure, move our webcam image. this figure represents the distribution with different numbers of success, or different probability of success. So if we are centered, we have a probability of success of 0.5, our distribution is actually going to be centered right in the middle, which is right where we expect. So our 0.5, all right? And as we drift, as we lose our probability of success, all right, we're going to move. But we don't just move. Our variance gets smaller and smaller and smaller as we approach the edges. So our variance is pretty wide when we're centered around 0.5 for our success. And then it narrows as we reach the edges. What's the implications of this? If we're working with a binomial trial and our probability of success is around 0.5, oftentimes we can assume a normal distribution. Even though this is an underlying binomial distribution, we might be able to assume a normal distribution to calculate probabilities, to calculate p-values. Would I recommend doing that now? No, I wouldn't. Not with the computer. This is back 20, 30, 40 years, actually, 40 years ago, when like the only computers were the mainframes, and some of the old people probably would tell you about a punch card. You have to like do like punch card system and slide that into the mainframe. I've never encountered it. I know Wake Forest had one. I never went down and looked at it because I had a laptop sitting on my desk. All right, but back in the day, it was much easier to assume a normal approximation. Why? Because we had tables. We had books of tables of probabilities of all of those. So that's when we can approximate a normal distribution. We're not. It's easy just to do our actual calculations. But for this distribution, we're defined by our total size, our out of number, and the probability of success. How do we use it? How do we use it? We typically use it as part of a goodness of fit test. So we go out and we sample, make some observations, and then we get a frequency table set up. And what we're doing is we often ask, is this frequency table, are these data randomly distributed? Is, sex of the offspring random in the clutch? Is the infection random in our pond, and so forth? All right, we have our actual observed values right here, but what we have to do is come up with an expected value. And if we can recognize that the outcomes follow a binomial distribution, then we can manually calculate the probabilities and our expected numbers based on this binomial distribution. So here's an example. All right, we went out and looked at all the prickly pear cactus in an area. All right, we looked at flowers. So we did this maybe spring, summer, recorded which of them had flowers. All right, tagged the plants. And then from those plants, we followed to see how many of those flowers actually produced the fruit. All right, and we're going to make it easy and say that each of the plants that we found, they had 10 flowers. So our total out of number is 10 flowers. And then we counted up how many of these individual cactus produced 0 fruit, 0 fruit, how many had 1 fruit, how many had 2 fruit, 3 fruit, all the way up to 10 fruit. And this is what we have. So total number of plants that we observed represents the sum of this column. This is just a basic frequency table. Now what we're interested in doing is trying to figure out, well, one, what's the average number of fruit that we have? Well, we can convert our data to a vector and calculate that. Right? And then the next step would be, once we have that, we've got 2 questions. Is the fruit set, number of fruits per individual, equal to some value? So maybe last year we saw 7 fruit. Right? We can compare it to that value. Or we can ask the second question and just ask, is fruit set random across this sample of cacti? So first up, go ahead, convert this frequency table into a vector. Let's do that in R, and I'm going to show you how we kind of calculate probabilities and then expected values. vector fruit. How'd you get it? Good? So, fine. So instead of creating two different vectors, I just put it all in one. So here's my x values. So 0 to 10. What's that? The shortcut, right?
Yeah.
You learn it. And then that's the frequency. That's our frequency called. Okay. I used the rep function to get there. All right. And then I saved it as fruit. And then just as a check to make sure that I did it correctly, I did table fruit, and it should take me right back to my frequency table, which is what we want. All right. So what can we do with this vector? Well, we can calculate the mean. So I did do the mean, and I have a mean of 5.0025. It's pretty good, because I do think I probably created these data with the mean of 5. Right. How do we get the number of successes, or the probability of success? So our mean is n times p. We want to know this because if we're going to generate probabilities and expected values, we need to have a probability of success. But we know what our average is. Our average is going to be whatever the average of this vector is, right, which is 5, pretty darn close to 5. But we want that. Well, what if we do our mean divided by our out of number? Would that give us a probability of success? Yeah, it will. It will. All right. So we can then use that to calculate our expected probability column. All right. So we're going to take what we have. All right, so we're going to say 5. We're going to round just to 5 and say that's what our probability is. So P success is equal to our n divided by our mean. All right, so that is, that's the other one, mean divided by n. So we're going to say 5 over, what's our out of number? 10 fruit. That's our out of number. So that's going to be our probability of success. And then what we're going to do is use the dBinom function to figure out what our probabilities are. All right. Now, what we want is a probability of getting 0 out of 10 fruit, probability of getting 1 out of 10 fruit, 2 out of 10 fruit. 3 out of 10, 4 out of 10, and so forth. So what we're going to use is this dbinom function, and we are going to pass this vector 0 to 10 as our x. And R is going to do it one by one. It's going to take the very first value, do the dbinom. Our out of number is 10. Our prob is 0.5. We just calculated it. So it's going to do this function for 0, and then it's going to do it for 1, and then 2, and then 3, and do it all the way until it gets to 10. So when you get it, here's all of our values. That's all of our probabilities. All right. So then our next question is, how many plants did we study? How many plants did we study? And why is that important? How are we going to use it? So we have our probability, all right? But we need to know the expected numbers, because if we go back to our table, when we run a goodness fit test, we have an observed and we have an expected column. How do we get our expected? Well, we got our expected from the probabilities, but these are just raw probabilities. The sum of these probabilities have to equal 1, right? And they will equal 1 here. What we have to do is take those probabilities and convert them to actual expected values here. So we need to know how many plants we actually studied, because then out of that total number, 0.00098 of them, or that proportion, right, should have that 0 fruit and then 1 fruit. So how do we figure out how many plants we have in this study? What's that? Yeah, length of fruit. What is that also called? A sample size. So here's our sample size, right? So we have 2,000. We studied 2,000, which means, whoops, typing it on the wrong one. Length of fruit. So I'm going to say this is our sample size. All right, so now we want to ask, how many plants do we expect to have 0 fruit and 1 fruit, and etc.? Well, we could do it one at a time, or we can do all at once. So I'm going to grab this. There's our probability. I'm going to copy it. I'm going to paste it down here. Oops. Where did I do? Paste it all. Let me do it again. Copy. Paste. So there's our dbinom, and now I'm going to multiply our total plants, which was 2,000. And when I run it, now I get my expected values. And now from here, we can run like a goodness fit test, you know, chi-square test or a g-test and so forth. And that's what's on this table. That's what I did there. Not too bad. I mean, this is our application. This is how we would use it. All right, so how do we use this binomial test? How do we, you know, what are we doing with this? One is the test for randomness of data. All right, so is our data random? Is sex random? Is fruit set random? All right. In order to do that, we have our observed, and then we calculate expected probabilities, assuming that it is random. How do we assume that? Well, we use the binomial distribution. That is, inherently random. Now, if we do that, then P is going to be calculated from the data, just like we did. We calculated the mean of our data, that was the P, and then we said, okay, well, if this P is equal to 0.5, then these are the values that we should get. All right? The other one is to test that the probability of success is some value. So we collected our data, this was the table, all right? And maybe last year our probability of fruit set was 70%. We can compare what we observed this year to last year's data using that probability of fruit set of 70% to get this expected column. And then again, do a chi-square test, goodness of fit test. Both of these are hypothesis tests. Right? Both of those are going to compare our observed to expected and generate a probability that we would actually observe data as extreme or more extreme than what we observed if our null hypothesis is true. And we'll do some of this. We'll do some of this later on. The other one, and the ones that we're going to focus on right now, is just a straight up probability. So calculating probability of getting at least one fruit, or the probability of getting 3 or more boys and 5 children, or the probability that we have all infected individuals in a sample of 100. All right? That's how we're going to use this now, because we can't really do the hypothesis testing until we learn about these p-values and how we're actually getting them. But we will. We will. All right, so here's practice. So we have this table. This table has offspring number, right, where you can say an organism always has 7 offspring. Maybe it's true, maybe it's not. Who knows? All right. But in this example, we've only found 7 offspring in their clutches, and we recorded the number of males in that clutch. Okay. So what we want to do is calculate probabilities and expected values. And we're going to do it 2 different ways. So one, we're going to use the information in the data to kind of address that first question. Is our data random? And in order to answer that question, we have to calculate the mean of our data and use that to figure out what our probability should be. So you're going to calculate the probability column and then the expected number column. And that's the expected number of clutches that have 0 male and 1 male and 2 male and so forth. And then the second part is change it up and say, okay, we think we should have 5 males on average. All right. If that's the case, then what would be our probability of 0, 1, 2, 3, 4, 5, 6, 7, and how many clutches should have that many offspring? So what we're going to do is I'm going to let you work on this. All right. When you finish this up today, we're going to be done for the day. And then what we'll do on Wednesday is kind of look at this table, look at the answers and see how I would have done it in our markdown, make sure that we're doing it the correct way. Okay? So does anyone have questions? Those of you watching at home, just have this done. We'll review it on Wednesday, start of class.